Hi, our next lesson will be dealing with tangent lines. The objective is how do we solve problems using tangent line properties. So we have a diagram, circle O, and then we have a line that is touching it, which is BC. So with point of tangent and point of tangency, BC is tangent to circle A because it intersects the circle at exactly one point. So tangent means to a line or a segment that touches another shape, whether it be circle, square, tangent. So tangent is touching something else. So that means point B is called the point of tangency. So we have BC as a tangent, and the reason why it's a tangent because it's touching the circle at one point. It has to touch something, a shape or whatever, at one point. And that point where it touches is called the point of tangency. For our first theorem, it says that if a line is tangent to a circle, then it is perpendicular to the radius drawn at the point of tangency. So as you can see, our point of tangency, if I get the pen, actually I use this one, our point of tangency is R. So I'm going to put point R. So that's our point of tangency. Our perpendicular lines, which is OR and TR. They're perpendicular, and the radius is OR. And I'll put that in purple so that way you know. I use blue for that one instead of purple. So that will be OR is our radius. And I should put that as segment OR. So when you have a tangent line and a radius meeting each other, intersect at a certain point, the point of tangency, then they're going to be perpendicular. And I'm going to draw the little line to show you that that's perpendicular. So it says in symbols, or notation form, if line RT is tangent to circle O, then line RT is perpendicular to segment OR. So again, you see a radius and you see a tangent line intersecting with that radius in the circle, and it's always perpendicular. So for our first example, we have ED is tangent to circle F at point E. So point E is our point of tangency. So I'm going to put point E, so point of tangency. And they want us to find X. And our X, which I will highlight in yellow, is DF. That's what we're looking for. And I'll highlight this one too. All right, so in order to solve this problem, with the information that we know that ED is tangent to circle F at point E. So look at EF. EF is 3. EF is the radius. Why is it the radius? Because it starts at the center of the circle, which is F, and then goes to a point on the circle, which is E. So it's 3. That's our radius. And then we have our tangent line, which is DE, because it is touching the circle at one point, at point E. And then we're looking for DF. So if DE and EF are perpendicular to each other, perpendicular lines create right angles. And when you have right angles, that is a 90 degree, and it's a right triangle. So then this is a right angle. So now, with that information, we're going to look for DF, which is that side of the triangle. What are we going to use? We're going to use the Pythagorean Theorem, a squared equals b squared equals c squared. If you remember, with a right triangle, if they give you two sides, and there's a missing side, you're using Pythagorean Theorem. So then you plug in your information. EF and DE are going to be the legs, so it's going to be AB, or which way you want to switch it. But C is always designated for the hypotenuse. Hypotenuse is always opposite 90 degree angle. So once you plug that all in, you solve, and then you find x to be 5. So again, using the information about tangent lines and radius and knowing that they create a 90-degree angle, you can always find the missing side for that triangle that is part of that circle, or outside part, whichever, however the triangle is laid out. All right, let's go on to the next. Our second theorem says that if a line is perpendicular to the radius of a circle, then the line is tangent to that circle. So that's just the reverse. If you remember what we said for the other one, if a line is tangent to a circle, then it's perpendicular to the radius. This one is the converse, which is if a line is perpendicular to the radius of a circle, then that line is tangent to the circle. So that means TR is a tangent, is tangent to circle O. So in symbol form, you would write if line RT is perpendicular to segment OR, then line RT is tangent to circle O. And what strategies could we use to prove that that there is a right angle? Again, right angles. Right angles are found in right triangles. What formula is used to find sides of a right triangle, or if the triangle is a right triangle? We use the Pythagorean Theorem to verify if the right triangle is a right triangle. So with our second example, it says determine whether MN is tangent to circle, that should be circle L, so I'll just fill that in. So circle L. All right. So notice that they gave us, well, let's look at the parts that we know about the circle. We see that LM is 3. LM is the radius because it started at the center of the circle and then it goes to a point on the circle, which is M. So that radius is 3. And we notice that MN is touching the circle at one point, which is M. So that line is, our segment is tangent. And that tangent part line is 4. They also gave us ON. That's a segment outside the circle. That's 2. So how do we know if this triangle is a right triangle or not? We know that LO is missing, but we can find LO, and we know what LO is because look at LM and look at LO. LO is also a radius. So I'm just going to show it, to show the triangle with the missing, with the given information and what is missing. So LO is X, but we know that that is 3 because any radius in a circle is going to be congruent to each other. So if LM is 3, then LO is also 3, as stated here. So then we have 3. Now we know that this is 3. We're trying to prove if this triangle is a right triangle. But in order to do that, we need to use the Pythagorean Theorem. And we have LM as 3. We have MN as 4. Do we know what LN is? Yeah. The 2 that they gave us and the 3 that we determined because it's a radius and it's equal to what is given in that circle, which is 3. That will give us 5. So now we can plug in that information into the Pythagorean Theorem. Move this out of the way. Plug it in. Well, we found it to be 5, but we plugged it in and we see that this is 5 and it's going to be a right triangle. You can plug in all the information you need to find out if it's a right triangle. You put the 3, 4, 5 and then you see if it works, and it does. So this is a right triangle. So yes, MN is tangent. So again, going back to the theorem, if the line is perpendicular to the radius, then the line is tangent to that circle. So MN is tangent. All right, so the next one says determine whether BC is tangent to circle A. All right, so we have all our information. So I'm going to just separate it and have the triangle and all the information that they gave us. Again, if this helps you, especially if you're trying to focus on the triangle that is overlapping the circle and try to find out if it's tangent, if it's a right triangle, if the line's tangent, if you're looking for a missing piece, just draw the triangle with the information that they gave you and then take it from there. So I noticed that AB is the radius of the circle, so I stated the radius at 7. Then the tangent line, well, we don't know if it's tangent, so I'm not going to assume it yet. But it says BC is 9, so that segment is 9. And they gave us the whole length AC, but they broke it up into 7 and 7. 7 and 7 gives you 14. So I'm going to use those three sides, 14, 7, and 9, put it into the Pythagorean Theorem, and see if it's true. I did plug everything in, and I noticed that 130 is not equal to 196. So that means BC is not tangent. If you get numbers that are unequal to each other, then that line is not tangent. But if it all works in the Pythagorean Theorem, all the sides given for that triangle, then yes, it is. Then that means that tangent, that line or segment that's touching the circle, is tangent. All right, Theorem Investigation. So it says name two lines that appear to be tangent in the picture. Again, from what we know about tangent, tangent is either a line or a segment that touches the circle at one point. So let's see. It would be AB and CB, or BC, BA, however way you do it. And they want to know if the radius D, a circle D, is 8 units. So we got D over here. So that means DA and DC are going to be 8. And I'm going to put that. So that's 8 units. And BD is 17. So we got this part, 17. They want us to find the length of BC and AB. All right. So in order to do that, we know that this is a right triangle. We got that little marker there. And what's opposite the 90-degree angle? The hypotenuse. So BD is the hypotenuse. So we're looking for this missing piece, and I'm going to put it in blue. So we're going to put this piece X. But notice that whatever we get for AB, I wonder if CB is going to be the same. So whichever triangle we use, it's going to have the same side measurements. So let's look for AB. Okay. So basically, oops, let me move this out of the way. So I just drew the triangle, and I'm looking for AB, which is X, because that's the unknown. And we know that radius, 8 is the radius, and 17 is the hypotenuse because it's opposite the 90-degree angle. So I'm going to be using the Pythagorean Theorem, of course, and solve for the missing side. Again, A is one of the legs, C represents the hypotenuse, which is 17, and then I'm looking for X. Do all that work. Again, when you have a square with your variable, the opposite of squaring is doing the square root. So what you do on one side, you do on the other side, and you find X to be 15. So if I did that for the other triangle, for CDB, I will get the same thing, but CB will also be 15. So let me put 15. So this is 15. This will also be 15. So they say that if the two lines intersect outside the circle, we can conclude that their relationship, what can we conclude about their relationship? That AB or BA or BC are congruent. So with that, that leads us to our third theorem, which states that if two lines tangent to the same circle that intersect outside the circle are congruent from the point of tangency to the point of intersection. So two lines tangent to the same circle that intersect outside the circle are congruent from the point of tangency to the point of intersection. So as we can see in the diagram over there, we can conclude that, based on our investigation, that AB is congruent to AC. So anytime you see two tangent lines and they intersect outside the circle, those two lines are going to be congruent. All right, so let's look at an example based on that theorem. They say find x. Assume that the segments that appear to be tangent are tangent. So okay, so that means AD is tangent and BA are tangent. And so is AC, because it's tangent to both of the circles. All right. So with this one, I set up a relationship. So I said if AD is congruent to AC, and I'm going to use different colors for this so that way you can see this. So AD congruent to AC, and AC is congruent to AB, then AD is congruent to AB. So if those two tangent lines, tangent segments are congruent to each other, then you can set up the expressions that are given for those tangent lines equal to each other. Okay, set it up, solve, and then you find x to be 4. And there you have it. Okay. All right, so just before we do the practice thing, there was 3 theorems that we covered. First one was if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. So where they intersect is the point of tangency, and those two lines or segments are going to create a 90-degree angle. Theorem 2 says that if a line is perpendicular to the radius of a circle, then the line is tangent to that circle. So it's just the converse of what we did with Theorem 1, but we're just saying it backwards to prove that, yes, that line is tangent. And the third theorem, based on our investigation, that if two lines that are tangent to the same circle and they intersect outside the circle, then those two lines are going to be, or segments are going to be congruent. Okay. So we're going to do this practice. So it says refer to the figure that's on the right and name each of the following in the figure. So they say two lines that are tangent to circle P. All right, we see it has to be a line that's outside the circle and it's touching the circle at one point. So that means we have QR and SR. 2 points of tangency. Remember, tangent touches the circle at the point of tangency. So if we said that SR and QR are tangent, then point Q and point S are the point of tangency. 2 chords of the circle. Oh, this is going back to our previous lesson about chords. And what do they look like and where do you find them in the circle? So chords, again, have 2 endpoints that touches the circle at 2 different locations. So that means QU and US are chords. Name 3 radii of a circle. Radii is a plural for radius. Radius starts at the center and then goes to a point on the circle. So we have PQ and PS. And also PT. Because I know if you're looking at it, you see that the T is right there where the line intersects with the circle. So that point from P to T is a radius. Name 2 right angles. Okay. So what do we know about tangent lines and radius? If you have a tangent line intersecting with a radius at a point of tangency, then those 2 lines will create a 90-degree angle, and you have a right angle. So then that means that angle PQR and angle PSR are right angles. And this next one is name 2 congruent right triangles. Okay, so in order to find a right triangle, yeah, I'll use blue. To name the right triangle, you have to find the right angle. Okay, right, there's a right angle. Okay, so I see that triangle PQR. PR, and then the other one is PSR. So those are our two right triangles because you have the right angle right in there. The hypotenuse or hypotenuses in the two congruent triangles. So remember, the hypotenuse is always 90 degree, opposite of the 90-degree angle. So then PR, segment PR, is the hypotenuse for those two triangles. Name two congruent central angles. Okay, we're going to the central angles. All right, so let's look. So what do we know about central angles? Central angles start at the center of the circle. And then also it's formed by two radii. So I'm going to use the highlighter to distinguish. So this is, I got this and this. So we got this angle QPT, and then the other one, which I will highlight in yellow, we've got SPT. So those are the two congruent central angles. Why they're congruent? Because those two right triangles are congruent. The tangent lines are congruent. So therefore, that central angle is going to be congruent. And they're all related. Now they say name two congruent minor arcs. Remember, minor means less than 180 but more than 0. So what are our two congruent minor arcs? Arc QT and arc ST. Remember, if the central angles are congruent to each other, then their arcs, their arc measure, are going to be congruent also. And name an inscribed angle. So angles or angle. So let's see. What do we know about inscribed angles? That it touches the circle at one point, and then it creates an arc that it's created by two chords, and it touches a point on a circle. So let's highlight and see where we can find that. So we have that point here, and I'm just going to highlight that. So that means our inscribed angle is QUS, and that's the only one, the only inscribed angle. All right, so that's all the questions that they were asking you. Everything you just learned from Unit 7, you're just applying it. Sorry, not Unit 7, Unit 8. You're just applying it to. I just got missed. Actually, no, we're circle. Sorry, 7. My bad. Everything from Unit 7, you're just applying it and putting everything together, and also figuring out based on the vocabulary. So if you know the definitions of like what's an inscribed angle, what's a minor arc, what's a central arc, major arc, what's congruent, what's a right triangle, what's a radii, what's a chord, what's tangent. If you know all of that vocab and everything that's dealing with that, then it's easy for you to pick out the stuff in the circle and figure out what's going on. So again, you need to know the vocabulary and their function. Okay, so now we've reached the end, and I already talked about the 3 theorems. About if you have a perpendicular, if the line is tangent to a circle, then it's perpendicular to the radius. And the inverse is if you have a perpendicular line, that the line that is perpendicular to the radius of a circle, then the line is tangent. And also, if you have 2 tangent lines that are intersecting outside the circle, and they touch the circle at one point, a point of tangency, then those 2 segments, the 2 tangent lines or segments, are going to be congruent. All right, so this ends our lesson. And again, if you have any questions, feel free to email me. It sounded like a tongue twister, and I will help you out. All right, have a good day.